Welcome everyone to the Type System Foundations for Supercharged Semantic Code Search by Ishan Bhanuka. We're glad Ishan can join us today. So without further delay, over to you, Ishan.
Hi everyone, nice to have you here. I can't see any of you, but I'll hope to keep you all engaged and drop some type system magic here. So hi, I am Ishan and I will be presenting on type system foundations for supercharged semantic code search. And I'll walk you, like, it covers a lot of interesting details around how a type system can allow us to search for things, which most tools do not use right now. So a little bit about myself. I am currently an independent consultant and I work mostly on high performance, like performance optimization and compiler related problems. And this work is based on a lot of my research that I did for my master's thesis and which got accepted at UPSLA 23. The type system, a lot of the core type system stuff is based on that paper. So let's see. What is code search and why do we need it? So if I could get a quick poll, how many of you have been airdropped into a large code base? And this is what it feels like. You do not understand anything, or it's very complex, a lot of details. I can't see the poll, but I hope you get the feeling. Yeah, so a lot of people feel that way. I feel a lot like this. But usually with time, like after getting a little bit familiar, we can kind of identify. For example, in one of the last projects I was doing, I had to refactor a single API in a server that was serving over 100, 120 APIs. So I had to isolate the logic related to my changes down to one sliver of the overall data, of the overall code. And to do this we use I'm sure this is like the most obvious, the most popular approach is to just do text search, either use regex or just do text search. So our IDs or text editors allow us this very basic functionality. For languages that are more functional or have good type systems, they allow us some basic form of semantic type search. For example, the benevolent Google. Using that, I can find functions by their type signature, which means that I have some amount of like this search understands the program a little bit. It can understand what the program is taking as input, what it is returning, and I can search based on that. I think this is a low level of semantic search because we can do much more than that. And then there's some cases which I haven't used personally, but there are cases for rewriting code in specific patterns where I would want to search based on the abstract syntax tree or the AST, and search for specific patterns and rewrite them. But I propose that there's another way, and I will call it data flow based semantic search, which combines all of these into into like something that's supercharged, and that allows us to find and change many things. And this is inspired by real world examples. Like I was working on a PR where I had to change where one change in one of the functions resulted in 82 files being changed, because that function was a very core constructor used in many places, and changing its return type changed over 82 files. But to make that change, it took me like 5-6 hours and just regex and vim macros, very repetitive changes across the files. Even LLMs couldn't help me here, which I'll come to later. But why is this the case? Because it's that the code is made of a hairy mess of entangled logical flows, and not that hairy mess, this one. So it's like a bunch of entangled wires, and I want to specifically find out the one wire that is relevant to me. I want to follow it through this entangled mess, right? So let me show you some examples now. It's time for a little bit of a live coding thingy. Let's hope it works. Okay, so let's see. Oh yeah, suppose I'm airdropped into this program. Okay, this is very realistic. I have some configuration for some kind of network program, and I want to find out, like you can see there's four keys to, like, I'm using a reduced subset of OCaml because that's what the type system supports. But try to follow along, even if you don't know the syntax. This is like a network program where I have some configuration related to try, retries, network adapter, blah, blah, blah. I'm doing some kind of validations and I want to check, okay, I want to check this debug mode. I want to see where is this being used. And right now, if it were a simple code base, I could just find it. But if it's more complex, spread out across multiple files, how do I find it? So I propose that we have a tool of like, there can be a tool, and there is a tool now in front of you, which is like, I think the first time it's being demoed, where I can do some kind of search on the semantics of it. I can, what I've searched for is that I have searched this code, this file, for all the logical flows, all the logical wires, or you can think of it like strands of computation that are flowing through the program. And I have searched for all the flows that are related to a tuple and its third argument. So you can see that it's showing me only those lines of code that are relevant here. You can see that it shows that the value true starts from here. It is wrapped into the tuple. The tuple gets applied to the validate timeout function, and so on. I'll cover the exact data flow representation here, but the idea is that it has isolated for me a very specific part of the program. And just to show you what all else is going on in the file, you can see there's a lot more stuff. There's a lot of stuff. There's almost 11 data flows here, but with simple queries, I can narrow it down to what I want to see actually. Okay. I hope this makes the case. And if it doesn't, we have small pause, questions or thoughts. We can, like, I'll have such breaks here so that you can take some time to think of what you've seen and ask questions if you want to. Couple of minutes.
Yeah, if you have questions to ask, you can raise your hands so that I can allow your mic, unmute your mic. Yeah.
Looks, oh, there's something in the chat. Maybe. Okay. Okay. So looks like there's no questions. So we'll move on to like, now we'll board the type train. So bear with me. We'll go through some of the type system details because I think it's really like, it's essential to know how a small change to the type system makes this happen. So coming to one of the most popular type systems is that Hindley-Milner, which is the basis of OCaml, Haskell, and even to some extent Rust. Internally, what it does is something called unification. And I'll show you why unification doesn't help us find that information that I just showed you. So unification is like the mathematical equality we have. A equal to B means we assign the value of, not assign, but we say that the values of A and B are equal. So for a simple program, like what is the simplest program you could have? You could, I created a variable and I assigned it a value. So when I created that variable A, I don't know its type. At that moment, I don't know its type. So I give it an unknown type or a blank or a fill in the blanks, and I call it a type variable. And when I see 1, then I know that 1 is an integer literal, and I can call it, and I can give it the type integer. But when I actually assign 1 to the variable A, then I know that I can say that the type variable for A is equal to integer. And that's how unification works. It finds relations between types and unifies them together, equates them together. It says, oh, these are equal, and so on. It keeps equating things until it either finds an error or the program type checks and passes. Right. So coming to a slightly more complex example, where I have 2 type variables now, and the same intuition follows here. But notice that the type variable B gets equated to the type variable A. So B says that whatever A is, I will also be that. And then we say that, oh, A is equal to an integer. So the type variable for A must be an integer and the type variable for B must be an integer. This way, unification changes the types across the program. Like if I have a variable A and it's used in multiple places, all those places will be assigned the type integer or some other type, whichever one we can infer from the program. But there's something missing here. It's that we lose out on the information. In Hindley-Milner, there's no way to track why the type variable b got assigned an integer. It just got assigned to it. So that's where we need something more powerful. And that's where the data flow, in the intuition of data flow, comes in. So for example, in this small program, even that's data flows is often how we think of stuff, but this type system tries to formalize it. So let's try to understand an intuition for it. You can see that the program starts with an integer literal at a certain program location. So L marks the program location. It says that 2 is here, and 2 gets assigned to x, the variable x at location L0, and that variable x gets used in the then expression, and it gets returned from the then branch of the if then else expression, right? So we do this often, except there's no tool for us to that helps us do this right now, especially when the code is complex. And notice that there's one other flow here, which is the else branch, which is a string, and it flows into location L3. So people who might be familiar with OCaml will immediately notice that this will give a type error because we have an integer and a string flowing into the same location, right? And that's fine. Like, we still have data flows. Data flows can help us find errors and do semantic search. If the program does not satisfy the condition that the types are correct, then we can use this information to present beautiful type errors, which is what the original research was based on. But so coming back to the type system and what it is actually doing, this is like, you can consider this the most important slide or the most important takeaway of the presentation of this specific type system. It is that I want you to think of programs as producers of data and consumers of data. Every single value is produced somewhere and consumed somewhere. And visually, you can think of it as type A is being produced at location P0. Can you see my pointer?
Yes.
Maybe. Yeah. Okay. So type A is produced at location P0, and it is consumed at location P1, which expects a type T. Everywhere in the program, this is what happens. And we can, and I want to formalize it using something called a subtype constraint. This is very similar to, remember, this is very similar to the equality, except now it looks like an arrow. And it's an arrow because it has a direction. It's saying that A is flowing, P0 is the producer of A, and A is flowing into the location P1, which is the consumer of A, and it expects a type T. If A and T match, then the program will pass. Otherwise, it will give a failure. So what do we do with this? This is just the smallest thing, the smallest notation here we have. Let me just erase this. Yeah. Okay. So I want to okay, this will be the most dense part of the presentation, but I want to walk you through how we can use this constraint in an if then else expression to find the data flow. Okay. So this is some of the notation here. Like, this comes directly from the type system itself, that we have program locations and we can join program locations together, because a piece of data can flow through multiple locations. We have some types and we have a state. Think of a state as a bag in which we store the constraints. Remember, we established that this is a constraint. We want to store them. That is how we can track the data flow. So we are carrying a bag around and we're storing stuff there. And this is the if then else expression. And remember, if then else expression has 3 expressions in it. One is the condition, one is the then expression, and one is the else expression. How do we type these? We start here and we first identify we take each of these expressions and type them recursively. And next, what do we do? So E1 was the condition, right? And for any if then else expression, the condition has to be a Boolean value. So here we can say that we can constrain it. We can say the type T1 should be a Boolean. The type T1 should be consumed at a location that expects a Boolean value, right? And similarly, the then and else expressions flow into the larger if then else expression. And we say that whatever, we don't know the type yet, but we can say that whatever it is, they must be the same. So the then expression T2 type and the else expression T3 type must flow into a type that is the same thing. They must be the same type for the program to type check, right? And using this, the type system can now collect all the data flows together. In fact, each variable, that is, each variable usage creates a new type variable with a new location. But then it can simplify them to give us a clean looking, like something that we can visualize very easily. And um, if the visualization fails for like if the type checking fails for some reason, it can be used to present a good data flow error message. For example, this one, which I'll explain, and then we'll look at more examples of how what we can see if it passes, right? So what do we have here? So just to pause here and take a look at the message on the right side. You might have seen errors because of this kind of situation many times. But this way is probably you've not seen it presented in this way. So just give it a few seconds. What it's trying to say is that there's a program location which is getting assigned to a string and an integer at the same time, and that's not possible, like that's not allowed. um, and the message below it shows how it's exactly happening. It's showing that the value 2 comes from line 1. It's assigned to x variable. The x variable gets used in the then branch or the then expression, which becomes part of the return type of the whole if then else expression. But the else branch of the if then else expression has type string. And so these two collide at the same location, which is why we cannot type check this program and present an error. But what if it type checks and we can now see very interesting stuff here. So I want to walk you through some build up some intuition around what happens when we have programs that type check. Yeah. So yeah, let's see this one. The same example that I covered, I have a variable and it's assigned to X, and we just in a REPL, I'm just printing out X. So it's saying that, okay, 42 comes from here and gets consumed here. Like the REPL is like the REPL can consume anything. So it has type anything. It can take and print anything. What happens if I have something more complex? Let's see what happens here. Okay. Okay. Now we can see something more complex. There's more going on here. For example, it shows that there's an integer, which is the first argument of the plus function, and it comes from the plus function itself. The plus function is here, and the plus function's first argument is x, and x comes from the value, like x takes the value 42. Similarly, we can see that it also finds the um, like the second argument to the multiplication function. And it says that the multiplication, so this is being curried, but you can think of it like this, it's just waiting for the second argument to be plugged in and it can give the return value. And the second argument comes from the whole function of multiplication, which is applied here, which gets assigned to y into, and the rest of the part, like the y into is waiting for one argument, the second argument, which is the value 2. So this way it can find out all these locations that are relevant to a particular type, and this is just printing them out, but later we'll see how we can search on them. For example, I can search on it right now actually. um let's see. Okay. Oh, so it's showing some other stuff as well, but I can restrict it to, let's see. Let's see only the int or int x. Yeah. So this way I can even narrow it down to specific. So now now I've eliminated all the other integer flows, and I'm only checking and I only want to see integer flows that are related to the variable y. So this is a very powerful tool. Like, it's almost like a lens that I can use to look into only one of the particular strands or one of the wires flowing through the whole program, right? And okay, let me just comment this out. Let's see something slightly more involved. Okay, let's see an if then else expression. Let's see what it does. So this is again just taking a number and saying whether it's positive, negative, or zero. And let's see what it's printing. Let me go check for classify. Classify. Yeah. Okay. So what is classify showing? It's taking the number 42. The number 42 is being passed to the if then else condition, and it gets checked by the greater than operator. The greater than operator's type is shown here, and then it's getting compared with 0. So it can track the whole flow of the integer, right from where it's being produced. Remember, this is where 42 is produced, and this is where it gets finally consumed at the at the greater than operator, which has the other argument 0, right? So it can even track flows through functions. Right now we are inside a function. Remember, classify is a function, so it can go in. That's why it's more powerful than, it has more granularity than something like Google, because it can go inside functions. It does not consider function boundaries as barriers. It can go inside them and see where a type is being used and how it's being used. And let's see another example. Let's try to construct a tuple. So this is another one. Let's see what it says. Okay, what is this saying? So if you notice, this is the const function, which just takes a tuple of 2 arguments and returns the first one, which means that the second argument is not really relevant here, right? And that's what we'll see in the data flow as well. It just picks the first one, and it says that the first one is wrapped inside a tuple. It gets applied to the const function, and the const function's body is this, and this is its argument, where we get that first value we'd assigned, and it says that the body is this. Like, there's some glitch here. It should ideally point to this a, and it says that, okay, the first argument got wrapped into a tuple, which got assigned to the const function, and it's getting returned by the this whole expression is returning that value. So this is saying that 1 is equal to this one, right? That's what it's saying, that 1 is being returned by this whole expression here. Can have more examples. Let's see one where we can construct new, like this also supports creating data types. So a data type is just a function, like a circle of int means that a circle is a function that takes an integer as arguments and returns a circle. Like, that's the constructor. A circle takes an integer and becomes a full circle. So that's what we can see here as well. Let me find the flow shape. Oh, there's a lot of stuff here. Okay. Let's see. Let's use the tool here. Circle. Nothing matching. Nothing matching. Let's see function.0. Function.0. Okay. It's showing some other stuff as well. Yeah. Let's see here. Okay, here. So this is like it's not pointing it out clearly, but you can see that it's showing the definition of circle. Like, this full thing is the definition of circle, and it's saying that, okay, circle is here and it's applied to 5, which becomes one of the elements of this whole list. that list is applied to the map function, and so on. So you can see that here it's here it's being consumed. So here, like in a pattern matching statement, the circle is now being consumed. So this way it can cut through function, like it doesn't consider functions as boundaries, it doesn't consider data types as boundaries, because all of these are functions, and all of these produce and consume values. Okay, now let me actually, yeah, the implementation isn't perfect, so there's some issue here, because of which so it doesn't stop type checking. Let's see if it stopped. No, it's not stopping. Let me just close the server, comment it. E. Okay. Any other examples? Yeah, and this example that I showed you, so we can now go over this example in a little bit more detail. Um, yeah, okay. This example, yeah, this one, the one that I initially showed you, that's like a network configuration, and I want to specifically find out where the value, the third argument of the tuple is being used. So again, here you can see what's happening is that it can, and I can even do search, like suppose I want to see all the places where the values of this tuple is being used, but I want to constraint, like I want to add another filter that I want to see where are the if then else conditions. No, if then else expression. Okay, maybe this isn't working. Maybe this isn't working right now. Bool. Okay, so I can do it by checking for Boolean values. So you can see that I could remove all of it and focus on a specific flow. And one of the most interesting things about this is that this approach combines the type information with the syntactic information, because let's see here, these locations that I have, in fact, going back to the original intuition here, P0 and P1 are program locations, but they can also be locations in the abstract syntax tree. And then the abstract syntax metadata from the abstract syntax tree can be used to enrich or can be attached to the type. That way, we can combine, like this approach can combine semantic information about types and syntactic information. For example, that, oh, this type comes from an if then else expression, or this type comes from this variable name from the source code, and things like that. So it can combine these two to make it, again, supercharged search. Okay, questions? Any? I hope there are no comments, no questions. Okay, cool. People are, I guess, dumbfounded. That's something so powerful. What is this? Okay, yeah. So, like, why were we doing all of this? Like, why finding this, all this constraints and all? So, going back to an intuition or like an analogy here, it's like, I'm trying to.
Sorry, Ishan. There is one question in the chat.
Yeah.
Do tracing or debugging tools already exist to trace values through call chains?
So they might do it at runtime. Like you can have tools that can do it at runtime, but I have not found a tool that can do it at compile time. Yeah. So the idea for like tracking all these constraints was to create like a park, like visualize a park where there are many paths, and types can walk along these paths to various places. They all start at the entrance and then the exit somewhere, right? And for a program that type checks, all the values walking on in a particular park will be of the same type. Otherwise, they can bump into each other, and if they're not the same type, then it will be a type error. So you can see this is like some just hypothetical, but a hypothetical graph for a very simple kind of program. The Boolean throws into if then else condition applies to not operation. One of them gets consumed in the REPL. One of them I print out. But there's something more going on. Some places a boolean does not directly get applied to the print statement. You saw it in many places where a particular value got wrapped up into a larger type. So we'll call these constructor types because they take a type and construct themselves. Like they are not complete without another type. A tuple needs two types to be fully constructed. So you can see that the not operation, after the not operation, the boolean gets wrapped into a tuple, and then it's the tuple that's moving around. It's the boolean is just being carried with the larger type. Think of it like you enter a park, but when you exit, instead of walking back, you take a car or you take a taxi. So now it's the taxi that's moving, and you want to track the location of the taxi because wherever the taxi goes, you'll also go. um, so this is like a layer. You can think of it as layers of a graph. The first layer of the graph is only related to you walking in the park. The second layer of the graph can be you moving around in a car. Maybe that car drops you off at the airport. So the third layer of the graph would be you taking a flight. And the idea is that these wrapper types or these constructor types by themselves, like they carry along types with each other, but because they carry along types with themselves, and some place they're destructured, we need to track them as well. Otherwise we lose. For example, if I see you exiting from the park and you take a car, but if I cannot track the car, then I will not know if you reached home or not, something like that. So we need to track the wrapper types as well, which is what this particular approach does. It can track like the data flows through these constructor types as well. And what we get by creating this graph is now that we can find straight line or linear paths. We can linearize the data flows as straight lines. And the moment we can convert them into straight lines, these red lines, for example, now I can do something as simple as regex based search. So the notation that you saw that I was using is something like a regex for semantic search, right? I can search. I can say that, okay, if I have a name, I have the name of a type, find me all the data flows that have that type in them. I can also ask for constructors. I can say, okay, find me all the data flows that have tuples, but the flow is related to their first argument. Or I could do some kind of check on the AST, like the metadata of it. There's one other very interesting case. Like this will come to the initial example that I showed you about that 82 file PR that I was making. We can also check for the in degree of the type variables. For example, this if then else condition here, this if then else condition has two different Boolean values flowing into it. And this becomes very relevant because remember this example, which kind of inspired this whole approach, that took 4 to 5 hours to solve. Well, actually, in semantic code search, if like it can be expressed very, very easily in like a very concise manner. It can be used to express all the locations where I need to make the changes. Think of it like this, that there's this big function call graph, and I have constructor one whose type signature I've changed. It was returning a result. Now it's returning a unit. So now I need to change all the places where constructor one is used. Right. So constructor two uses constructor one. So it will also change. But there's a difference. This logic type here, this logic function here is does not change its type because like it should not change its type because its type comes from two different functions. So one function alone, like I like logic is not getting its data from just one function. So its return type is not decided by one function. It is decided by both the functions, which is why its type should not change. So why is this powerful? Because with semantic search, I can find the locations relevant to my changes and even feed it to an LLM. For example, in this 82 files, there's no way right now some local tools like all these cursor and Claude and Copilot, I cannot give it an 82 file context and ask it to make the changes. But if I can use some kind of search to find the specific locations and add them to the context, then it makes it so much more powerful, and I can make targeted changes using an LLM. So this is one other application of semantic search apart from just understanding the code. And to go back to the to how would this be solved? So I can ask a query saying, okay, find me all the data flows where constructor one is used. It returns a result type, and it returns a result type to a type variable where it is the only thing flowing into that type variable. And at function one means that type variable then flows into the return type of a function. So what I'm asking here is find me all the functions where the return type is only decided by constructor one. Using this query, I can find the specific flows. Again, the implementation is not perfect, but the type system and the information being captured by it entirely supports this. So taking a step back, what were we discussing this whole time? We were trying to untangle data flows in a program into neat paths that we can search upon. And once we can search them, we can use it to power all kinds of tools. There's a lot of future work needed for this that I'm currently working on. One of them is to support type classes. Type classes don't fit into this neat analogy and neat diagrams that I've shown you, because type classes operate at a higher level. They don't fit in this graph diagram. They have to be supported differently. And semantic search itself needs more operators and better visualizations. Right now, if you notice, I'm supporting 4 basic operators, but more powerful operators can be built on top of it. Yeah, so this was research done during my master's, and the paper for the type system is publicly available along with the GitHub repo for it with the demo, and the semantic search part that was built on top of it later. I built it with my collaborator Mahir, and it was super fun working on this. And if you want to collaborate, chat, or hire for performance optimization or compiler stuff, these are where you can find me. And I have a bunch more slides that I can show you, but it'll be good to use them to answer questions rather than dump more notation. So yeah, thank you, and quick questions.
Yeah, if you have any questions for Ishan, you can put it in Q&A section or even raise your hands.
Looks like no questions, so I'll be hanging out in the Hangout or Meetup spot, and we can chat more.
Yeah, thanks Ishan for the session.